Okay, so we're gonna continue with the MATLAB, second MATLAB lab. Which is lab 4, lab 4. And we messed around a little bit in FreeMat to kind of demonstrate some of those things. So you can bring up FreeMat again. And you put your demo script in a folder, and you gave it a name like Lab 4 with your initials. And we started something like that to kind of get things going. And my goal is to kind of get you set up so that you kind of have a sense of how to finish it and walk around and kind of clear up any confusing areas that you might have. But just want to see if everyone's kind of got the basic thing up there. Is anybody not here on Tuesday? Okay. One person? Anybody else? 2 people? You know what I'll do is I will post this to, I'll make an announcement on Canvas in the class, and you can pick this up and dump it into your own FreeMat window. So that will speed things up. Let me see. So if you go to the announcement, you can pick this script up and just copy this thing. And you might need to refresh your announcements thing, but copy that. And then what you'll do is when you have FreeMat open, the trick is you first need to navigate your folder pointer. And that's where you click this yellow folder, you choose the directory, and you should go to your desktop. And you may have an Engineering 1A or a MATLAB folder, something that you remember. Select that folder, and then in FreeMat, you would make a new file, and then you'll paste that file, paste the contents of what you just did in there, and it looks like some weird formatting took place. Did it screw that up for some reason? I don't know. What you might want to do is, gosh darn it, I think I might have gotten some formatting issues in there. So anyway, you can't win. Stuff always messes up. But that's the idea. And if that doesn't work, what you can do, if you can bring up Notepad, like if you go to the command window and just type Notepad. Notepad is a good thing to filter out strange formatting characters. So you just paste it in Notepad and copy it from Notepad. And then when you go to the place you want to put it in, it wipes out any of that stupid formatting junk that screws things up sometimes. So it'll look like that if you had any problems originally. So what that is, this is a script now, and what we're doing is we're putting all of our commands in here because it is a more effective way to develop code than just typing it at the command line. And let's pull up the lab gun. And again, what we're going to do is we're going to produce a number of plots of the decay of some radioactive materials over time, and we're going to use these formulas. And there's some things here that might be kind of blowing you away if you haven't done a lot of this kind of math yet. I don't want people to freak out. You're not going to be having to do this on a test. This is just an exploration of what it's like to be an engineer. So, you know, we stretch our minds a little bit and get exposed to these things. So we know how to raise a number to an exponent, right? Do you remember how to do that? Yeah, you can do the caret command, right? So E is a special number. It's like Euler's constant or something like that. And you can say like E, and the number is 2.7183. It's a special number, kind of like pi, which everyone knows, 3.141. So it's a number that you can then take and raise it to a power. So if you say E to the third power, you get 20-something. And so you're going to come up with a formula to compute the parent fraction, which is how much of the original material is still present in the sample. And the daughter is how much of the decayed material is present in the sample. And then you have to compute the log of 2 over t, which is the decay parameter. So let's do some of that. And what they're saying is you're going to create variables for the constants in your program, namely the parent isotope amount, P0, and the half-lives for each isotope series. And initial parent isotope amount is 100 grams. And then there is is there a lecture on this stuff? Let's see, lab 4. In lecture 4.5, you can pull up this link on some of the plotting commands. We kind of went over some of those already. And the scripts. And we talked about logarithmic plotting. And there's this other function called log space, which I think we might have touched on in the first lecture. I'll actually just explain that to you pretty fast. So remember we talked about the value of logarithmic plots, so the semi-log x thing and the semi-log y, and how to do multiple plots in a curve. So plotting 3 things. Would you like some more? I probably should give you some more hands-on stuff about these are the building blocks for this lab, and I'm kind of hoping that I'll show you the building blocks, and like a system engineer, you would put all those pieces together to make the program for the whole thing. That's sort of my goal. So I don't want you to just type what I'm typing, you know, like I don't know what you're doing, but I'm just going to type it and get through the lab. I'd like you to kind of just spend some time making some mistakes and calling me over, and I'll kind of help you kind of clarify things. But eventually you're going to have 3 curves to plot, and you notice they're all going to have the same x values, and that's what in our case they're going to have all the same time values. And one of them is going to be like the one for rubidium, one of them is going to be for uranium, and one of them is going to be for carbon. And you can play around with these formatting types if you want. And but I kind of recommend that you find these slides. Do you want me to show you how to find these slides again? Because these are good reference materials for you. You can pull these up, and you're the engineer who's kind of looking up stuff and applying it to your script. That's sort of the goal for that's how engineers actually work. You don't have to understand everything, but if you can kind of see something, oh, I want to do a curve kind of like this, you can try out like this equation and modify it for your particular application. So again, this is in lecture 4.5, which I should have put in the lab, but it is, you just hit the back arrow here, the previous from lab 4, and it'll take you to lecture 4. And then you can open up these 2 scripts, the 2 presentations, one on scripts and one on plotting. So there's that. And let me give you a kind of a rundown on the command line. But what you're going to do is you're going to type stuff in this window when you get your final program. So we've defined 2 constants. This is the half-life of rubidium. This is the half-life of uranium. And you have to do like the half-life of carbon. And looking at your handout, you're going to continue on there. But let's just develop a couple examples here. So here's an example of multiple of plots that have multiple curves on them. So suppose you have a time vector that goes from like 1 to 100, and you want to plot like the sine and the cosine on the same curve. So you might make like a y1 variable, which is going to be like the sine of t, and a y2 variable, which is going to be the cosine of t. COS, you've seen those, I think, right? And what's the point of why am I putting semicolons after these? Anybody remember why I'm putting semicolons after? Yeah, if I don't use a semicolon, it's going to spit out those 100 values. I don't really care what they are. I just want them to be created, right? So if I do this statement without the semicolon, it just spits out a bunch of numbers, and that's kind of clutter, and I don't really want to see that. So I'll save the printouts for the stuff I really want to see. And that's not one of them. So I now have 2 curves, y1 and y2, and I want to plot them both versus t on the same plot. So what I would do is I would say something like, plot t comma y1 comma t comma y2 without any special formatting. I will get them on the same plot, and this is what they look like. Now they're not very smooth because the curves are undersampled, and we can fix those a little bit to make it a little bit nicer. I might, instead of making t go from 1 to 100, I might change my t to go from 1 to 100 and put that all in square brackets, and then multiply that times maybe like 0.1. So I'm actually going in smaller time steps. Or better yet, actually, this would sort of be a little bit make more sense. I can make t go from 0 in steps of, or actually, sorry, I know too much MATLAB. That's why this is confusing for you. 0 to 10 in steps of 0.1. You could do that too. But then you got to recalculate your y1s and your y2s, and then you got to plot them. And when you plot them this way, they'll be smoother. And they'll look more like the familiar curves you're used to seeing. And one of them's green and one of them's blue. And you can put a legend on them real easily. The legend command kind of automatically positions itself. You just say legend, and you're going to say something like, well, what's the first curve? What's the y1 represent? Anyone remember? Sine. So you do legend, and in a single quote, you're going to say sine, and then a comma, and then in single quotes, you'll say cosine. And you'll get a legend appearing to kind of help guide you on your plot. Whoops, where's that? There it is, sine and cosine. So that helps guide the viewer on the information that's being presented. So there's going to be that, plotting multiple curves on a plot, and doing some kind of formula calculations. And I don't know, how you guys feel? You feel like you can tackle this? Anyone kind of completely like don't know where to start? Yeah, question? You say
I just really don't get it.
You don't really get what we're doing?
Yeah.
Okay.
Like looking at the lab.
You don't know how to do it? Yeah.
It's like,
Well, if you feel like you don't know what's going on, part of being cool with engineering is being comfortable with that feeling too, and not feeling like you can't do it, but just to kind of sit with it and kind of plug around a little bit. So, so there's sort of like a boundary between what I can show you safely without just giving you an answer, so that you don't learn anything, and how much you have to kind of hunt around and get started. So what I think I'll do is maybe I'll write a few things to guide you, and then hopefully you can kind of get keyed in on that and sort of continue it and kind of finish it on your own. And then if it doesn't make sense, I can just walk over individually and maybe work with each group and kind of get them started on this. So let's take a look at the instructions, which are here. And so it says, so we're doing this. Do you kind of get, do you know what the exponential curve kind of looks like? Is this really kind of confusing? Should I sketch this out again? I think I did this last time. The exponential curve, so what e does. So actually, let's just take e to the minus t that we just calculated here. And let's just plot that. So we got this t variable. You still have this t variable. It's either 0 to 100 or 0 to 10. Here's my t. If I go e, raise it to the minus t, and make y like y3 equals e to the minus t, I'm going to get an error because, remember why I get an error when I do that? From last week. The special thing you got to do when you do things to do to each item in the array, like, yeah, you can use that weird dot thing in there. I don't expect, oh, what is that? Yeah, well, it's just some of the weird syntax of MATLAB, and then you can plot t and y3 and show this curve, right? And this is the classical decaying exponential curve. It's the same curve like if you take a cup of hot water and you track the temperature over time, how the water cools. It kind of follows this trend. It kind of cools rapidly at first, and then over time it kind of cools less rapidly and kind of tapers to some room temperature value. And that's an exponential curve. And that curve represents so many things in nature. It's just so useful for so many things. So it also represents the decay of like rubidium decaying into strontium, uranium decaying into plutonium. So over time, this is how much like uranium you have left when you start with a certain quantity. And the time scale depends, determines the time constant determines how fast that decay takes place. So we're going to calculate a curve kind of like this and plot 3 of those things for different materials. Does that kind of help you with the big picture of what we're doing? And we're just going to play around with the equations to kind of show you how it changes for different time constants. And the third part is we're going to do this on a logarithmic time scale because that's going to give us a better way to compare these curves because they're going to all decay at vastly different rates of time. And if you do it on a linear time scale, they're going to be kind of really hard to see. If you do it on a log time scale, you'll kind of see clearly what's going on. Maybe this isn't the best lab, but it's kind of cool to kind of see this, and it helps you understand maybe the application of some of the math you get into in your other classes. So, so again, here is the formula for P of t and the formula for D of t, and then this disintegration constant K is expressed as logarithm of 2 over t, capital T, right? And so we have to compute not e to the minus t, but e to the minus k times t. And k is going to be different for each of these materials. The k for rubidium is going to be different from the k for uranium is going to be different from the K for carbon. So we're going to have to calculate constants for those, or variables for those as well. So I called this HL for rubidium, and now I'm thinking, because what this really is the time constant. It's called the half-life of a material, and that we're using T there. So it might make a little more sense to change these to T rubidium and T uranium. And then the third one would be what? T carbon, right? T C, and that's going to equal, in the handout it says it equals what? What's the decay rate for carbon? You want to look that up? Oh, here it is. 57. The half-life is 5730 years. Now I'm going to put a little comment here to tell you how to solve this problem. So the next thing you're going to do, if you're going to calculate e to the minus, you're going to calculate this curve like 3 times. Well, what does this calculation need? It needs a P0. Did we have P0 declared yet? So let's do a P0 declaration. So there's P and PO. I kind of like O instead of 0, but PO. And that's just going to equal 100. And we put like a comment here that's in grams. And it's good to kind of put the unit after these numbers so we can kind of explain what these represent. So these are the half-lives in years for all of them. And P0 is the initial amount of material in grams. So looking at that formula, P of T equals P0 e to the minus KT. What is that? We know it. We can find E already. We already figured out what P0 is. What else do we need in here? Time and the disintegration constant K. And that's given to you here. So that's another formula we got to do in MATLAB. Now what they don't tell you is there is no function ln in free mat. It's called log for the logarithm. Okay. So you're not going to say ln to, you're going to say log of 2. So so here's a hint. So we're going to say, let's compute K. So you're going to compute, but you're going to have to compute a different K for each material. There's a different K for rubidium, a different K for uranium, a different K for carbon. So you're going to compute like K rubidium, K uranium, and K carbon. And a hint is going to use log of 2 instead of ln2. Because what MATLAB likes to do is functions that have parentheses around the argument, the thing that you're doing the operation on. And then the T is already given. You already figured out these T's, right? So you can compute those pretty easy. That's going to be sort of step 1. Now, step 2, I'm going to probably guide you through this one because it's a little bit weird. What else do we need? We got K now. What's the third thing we need to do this whole formula? T. And what does it tell us that T is supposed to go range over? Yeah, so we're going to create a time axis vector span 100 billion years. We're dealing with large numbers in these labs. The time axis as a vector of 1,000 points logarithmically spaced from 10 years to 100 billion years. And we don't really have any clue how log space works, but you might have remember how lin space works? Let's just do a simple example on comparing lin space and log space. Lin space, remember, suppose you want to have like 7 values that range from 0 to 10. Does anybody remember the command for that? Lin space 0, 10, 7. How many points you want, right? So that gives you 7 points, 1, 2, 3, 4, 5, 6, 7, and they're evenly spaced, and they're going from the start value, which is the first number, to the stop value, which is the end number. Now, if you're going to be plotting your data on a logarithmic scale, like a semi-log plot, semi-log x is going to be the plot command instead of log x. instead of just plot, instead of linear, sorry. Then it's better to do log spacing. Now, log space points are interesting. Let's do something here. We're going to say log space, and let's go from 0 to 1, and let's do 7 points from 0 to 1 in log space. Let's look at the results and try to figure out what that actually means. One way of understanding something is just to do a little test case and see what happens here. So what log space gives us is, and again, with these numbers, this is not what you're going to type in for the lab, but these numbers are telling you, this is where I want to start, this is where I want to stop, and I want this many points, right? So we got 7 points, right? And what's the start value? 1. And what's the stop value? 10, which agrees with these two, right? Wait. Huh? How is that? How am I putting 0 and 1 there and then going from 1 to 10? It's 10 to the what? So this is the exponent. It's not a log. This is the exponent of 10 that you're going to do this log space from, right? So in other words, when you put a 0 there at the beginning, it's going to be 10 raised to the 0 power. We all know 10 raised to the 0 power is 1, right? Steady. And 1 there means you're going to stop at 10 to the 1. 10 to the 1 power is 10, right? And you can prove that's right by changing that to, say, a 2 and see what happens. Actually, let's go from 1 to 2 and see if that makes sense. If you go log space of 1 comma 2, it starts at 10, right? And that's 10 raised to the 1 power. And it stops at 100, which is 10 raised to the 2nd power, right? See why it's log space? And then the reason it's logarithm, too, is that these numbers are not evenly spaced anymore. If you look at it, the difference between here and here is 14.6. The difference between here and here is like less than 10. So the separation is getting smaller as you go. Well, actually, it's getting smaller. It's bigger. Wait. Oh, no, I'm sorry. That's 4.6, right? To go from 10 to 14. 4.6. And then here we're going like 7. And here we're going 10. And here we're going from 31 to 46. We're going 13. From 46 to 68, we're going 22. And here we're going like 34. So the spacing gets larger with logarithmic spacing, which allows you to waste fewer points on long stretches of time in your curve, if that makes any sense. So that's going to be step 4. You're going to create a log space, a time axis. So you're going to create a time vector and using log space, right? So you're going to compute, this is going to be your next comment, you're going to compute t using log space. And how many points are you going to have in there? 1,000 points. So it's going to be something, something, 1,000. Log space of, something, something, 1,000.
So would it be 100 since you're using log space?
Would it be what? What would be 100? The last number?
Yeah.
No, the last number is still how many points, how many total points you want. And again, you can sort of see on the example, we did log space of 1, 2, and 7. And how many points did we get? 7. So that number is still the number of points you want in your sequence. Okay, so we're going to calculate the t vector. I'm not giving you the answer, but I'm kind of showing you what you're going to do. So you're going to say something like, t equals log space, figure out the beginning and end so that you go from, you're gonna go from 10 years to 100 billion years. And then you're going to calculate the decay curve, and I think they mean P, don't they? Let's see. There's the daughter curves, and then there's the decay curves. Oh, no, you're going to calculate those daughter curves for each of the isotope series, and in its own vector variable, perhaps name them D1, D2, and D3 for each of the decay curves. And this is where you get to kind of play around with coming up with a formula. And then the command, so let's actually kind of look at that. Well, what's that going to look like? Well, to calculate the decay curve, we're going to start by calculating the P curves. So, and it says, you know, you might call them P1, P2, P3, or PR, PU, and PC. So in this next area, we're going to compute, let's call it, you know, maybe you can call it P1, P2, and P3 for the different materials. Etc. And for this one, your equation is going to be looking like, now it's a little bit confusing again because the math notation doesn't always match what you know, what you type in MATLAB. So when you see something like this, you're not going to type P parentheses of T. You're just going to type P1 for like rubidium equals, and then you're going to type P0 times. So it's going to be something like, you know, P1 equals P0 times, and then continue that as best you can. And do that for the P2 and the P3 as well. Okay. And then you're going to compute the D, the daughter values. So you're going to compute the D1s, the D2s, and the D3s. And those are pretty easy. That's going to, the D3 is going to be P0 minus, you know, so like D1 equals P0 minus something. Well, just P0 minus P1 and so on. And then you are going to have all that. And then you're going to ready to plot it. Okay, so the plot command, you're going to experiment plot using the plot command. Okay, plot using plot of, you know, T, P1, and getting all, I'm sorry, D1, and getting all of the curves on one plot. And then do it again using the semi-log x, and you'll get to compare them. These dots means this is what you have to finish. This is not the complete thing. You got to continue. You know, you got to you know, finish this. So you have to do some thinking, and you got to interpolate what I'm sort of typing out here, and then you can do like a legend as well, like I just showed you for rubidium, etc. And that's basically it. So you got like about 20 minutes to do that. Does that help? I think you should have a better sort of orientation. So I'm just going to let you guys work on that and walk around. And, if you're stuck on anything, just call me over and I'll help you with each step. So each step you're gonna type under each of these comments. So right here, in order to compute k rubidium, it's going to be k underscore rubidium equals, you're going to say log of 2, and then what are you going to say? Divided by what? Which one? T underscore RB, right? For rubidium. And continue that, then you compute T and have at it. So there you go. It's an adventure. Just No, these are so those capital T's are, these are the half-lives, and the little t is a vector of time in years. Okay, so this is a number, this little t represents a sequence of numbers in years, and like each year that you have a value in your time thing, you're gonna compute how much rubidium you have. It's part of the calculation. But you're doing that all as a vector. I like questions, so please ask. Yeah. Uh-huh. And you know what? I will also paste this in the in case you want to just copy this from Canvas. I will paste this as well, if that works for you. So you can just copy all that from Canvas if you want to. Okay, if you're still drawing a blank, I want you to tell me so I can come around and kind of get together. And by the way, you don't have to all do it yourself. You can talk to your partner about it.
It's 10. Okay. So like, wait, what do we have to? We have to try.
Yes, log to the base 10. It is log. You can do the log to the base. And then you got to do just log parentheses to log parentheses to
We do our key underscore video.
So you know what we're going to do. So one thing you can do. And you guys can all work together. You guys are all good because you guys have some basic mathematics. It does. Yes. I think you just need it for that. Yeah. Star T. Yep. Okay, how you guys doing? Is this too crazy? It all depends on where you are in your math sequence. You've never seen it before. Okay. Yeah. Good. Yep. Good. Question?
I get this. But then we need like exam equations.
Yeah, when you're ready, you'll run it and it'll also run. Yeah.
So I still need to define which sentence.
You know what I could do is you know what I'm afraid because we only have 10 minutes that I would love to if you want to play around with this and just like leave and go this way. What I'll do is I'll take you through and develop like one of the curves and then you can try to do it for the other curves and we'll complete it. So you'll have one of them all the way done. And then I think once you see how it works for one, the other one should sort of make sense. So and I really hate typing all these things, but here we go. So t is going to equal log space, and what's the first number for t? We want to go from 10 to 10 billion. It's 1, right? Because 10 to the 1 is 10. And what about for 10 billion? Is it 11 or is it 10? 1 billion is 10 to the 9th, right? Isn't it 10? I think it's 10. I saw some people did 11. I think it's 10. And how many? We want 1,000 points, right? And a semicolon is going to suppress all those values. We don't need to see all of those 1,000 numbers. And so P1 is then going to equal. Oh, it's 100 billion. Sorry. So then it is 11. Thank you. It's 111, 1,000. Everybody got that? Okay. So then P1 is going to equal P0 times, and we're going to take E and raise it to the, but we got to raise it using the dot shift 6, right? That dot operator. And then we're going to use parentheses minus K what? RB times what? T. So that's your P1. And what that means is for every value of t, you've got 1,000 time values stretching from 10 years to 100 billion years. And for every one of those time values, you're calculating a p, you're calculating this formula for all of the different time values in this one vector. And does that make sense? That's the power of MATLAB. We're doing a lot of calculations really, really fast with a little simple expression. Because right, there's going to be 1,000 numbers in this vector. 1,000 values, and with this one statement, you're computing the p value, the concentration at every year in that vector. But I know, yeah, some people are just in algebra, and that's okay. You don't have to worry about it. It's just we're just kind of playing around here, and you're going to do the same thing for P2 and P3, and then D1 is just going to be the difference between what you started with and what you currently have. And then we're going to plot once using just a regular plot command, plot t comma d1, and that will show you at a linear scale what it looks like. And eventually you're going to plot t comma d1 comma t comma d2 comma t comma d3, but not yet because you haven't defined all those other guys yet. And then you're going to do the same thing. Well, actually, you can just activate the legend, and in this case, the legend is just going to have one thing in it. It's going to say legend, and the legend is going to say rubidium, or just RB. And then we got to do, of course, the X label, which is going to say time in years. And the Y label, which is going to say, what's the Y label going to have on it? It's going to have the daughter values, right? It's going to have the D of T, which is going to be in units of what? Grams. And actually, we might want to be clear about this. What we're actually plotting is not the rubidium, but what rubidium decays into, which is what? Yeah, which is what, SR? Okay. So we got all that in there. And when we click the green arrow, we're supposed to get a plot. And when you blow it up, it looks like, whoa, the legend is a little overkill. What happened to my legend? I don't know. So I'm going to kill the legend for now. Maybe we'll just worry about that later. Probably bring that back when you have everything. And let's just look at this plot once and see if it makes sense. So this is the decay for, this is the concentration of strontium when we started with rubidium. Over time, we're getting more and more of that material turning into strontium. And we haven't actually reached the end yet because it's going to go all the way up at the very end, 100. But over 100 billion years, we've only gotten to about 75% of the final, only about 75% of the original material has decayed into the decayed material strontium. But when you do that curve again for uranium and plutonium, that curve is going to go up sooner and sooner. But now this is actually a linear scale. So this is 0, 1, 2. These are all linear units. And when you put it on a log scale, it's going to look quite a bit different. So you can change that to then say semi-log x. And you could just ignore that plot or just copy this plot command and change that to say semi-log x. And let's look at what that looks like. And interestingly enough, when you do semi-log x, it's showing you a quite different curve here. It's showing you, wow, everything's really flat until you get to 10 to the 9 years, 10 to the 10 years, it kind of starts ramping up. That's the same numbers, but they're plotted on a logarithmic scale as opposed to a linear scale. Does that make sense? Well, let's actually look at this thing. What this is saying is, if you look at this chart, it's saying, when you get to 10 to the 10 years, that's giving you a concentration about 10. So 10 to the 10th, so 1 times 10 to the 10th gives you about 10 grams of strontium right there, right? But this curve doesn't look anything at all like the curve on the linear chart. But are the numbers the same? Well, let's see. You got 10 to the 10 here, you got 10 there over 10 to the 10 years. Well, let's look at that back on the regular linear chart. And to do that, we're going to just comment out the semi-log x command and do the plot here like so. And very interesting, but when we go to 10 to the 10, what value are we at here? At 1 times 10 to the 10, we're over here. Oh, look at that. That's interesting. 10 to the 10 on the linear chart is putting us right here about 10. But this point here doesn't appear on the semi-log x chart until you get to way over here. Because of the way the axis is stretched with logarithmic scale. And this is kind of funny because, yeah, I can imagine if you're in a class where you haven't actually come across logs yet, this doesn't make any sense at all. But when you do get logs in your like Algebra 2 class, you go, oh, that's what Weevil was talking about in that engineering class. I now get it. But the timing seems to be different for different people because it depends on where you are in math class. But that's okay. We're all just doing this kind of for fun. So I'd like you to continue that by doing the rest of the curves, and you could do that in 2 minutes if you understood what was going on. Do it for the other curves, and then you get all three because you're going to type in like t comma d1, t comma d2, t comma d3, and you'll see how they look on a linear scale versus a log scale. People are stunned, right? It's just like all the fireworks are going off in your head. You've like seen the way the universe works. And you can still tell the overview, still kind of rough. Yeah.
Did you get everything?
I think so. I didn't feel the man, but I got to what he outlined for us.
What you do, and it's is you just go to this first
He posted it in the announcement today.
How do I change those?
You have to put each of the
Oh,
short that's all and comma.
and then just put it again. There we go.
Oh, yeah, it's good on.
You know what? Yeah, it's a weird process.
There's only supposed to be yeah. Oh yeah, yeah, yeah. To do like the function, Python has a small aspect. So I might be on there. Kind of like what if I completely get rid of this?
You have to come through in this office first.
Oh, dude, did I just run in for the championship for the ranch at the and see, I already know that. I just checked. I just checked out. Really was doing this season. Gary got more than he does. He's back.
Did you get 3 curves and they come up at different times, right?
They're all like the
Yeah, yeah, that's it.
red ones all the way up like the back.
Yeah, yeah. That's how, and the log scale kind of shows it much clearly where they kind of sort of kick in. Yep,
So
that's
this
good.
is all I need for the lab?
That's it.
Just the lab report, right?
Yep.
Okay, thank you.
Yep.
Yeah, I saved it all. Mine would say it's base. Now, using a quick assist, you can reverse that around, switch it around. So this is basically
Which will answer that.
these are the variables. Basically the division of
I did the CAP internship at NPS the past 2